recording here. So section 4.5 is graphs of sine and cosine functions. Oops. Didn't mean to move it. Okay. So if you think back to Math 126, right? So in Pre-Calc 1, you would have talked a bunch about graphing. And before we graphed, before we knew what y equals x squared looks like, or y equals the square root of x looks like, before we knew those basic shapes, one of the things that we could do with graphs is we could plot points. So you could, if you wanted to plot the points for the sine graph, plot the points for the cosine graph. So we're going to start with the sine graph. So I'm going to start off by kind of showing you sort of where the sine graph comes from, and then we'll go from there. We'll see what happens. Okay, so we're going to make a table just like we used to do probably in Math 126. So here's the x value, and we're going to look at y equals sine x. And so when we're doing this, as opposed to other functions where we might plug in 0 or 1 or -1, we're dealing with sine. So we want to pick things that are nice, and things that are nice are things that are on the unit circle. So for instance, if we look at 0, this would mean we're looking for the sine of 0, and the sine of 0 is 0. If we were looking at my next one, say pi over 6, so we're going to find the sine of pi over 6. So anybody know what the sine of pi over 6 is from last class? You're all yeah, 1/2, right? So, you need to, just so that we're clear, right, for the test, our first test is 2 weeks from today. So, for the test, you need to know that unit circle, okay? So, and you're going to have to give on the test exact values. So even though you can plug things into your calculator will not give you exact values. So you're going to have to know the unit circle for the test. So you have 2 weeks, right? So if I were you, I would work on trying to learn that now rather than wait a week and a half and then only have a half a week to be able to do that. So just kind of put that out there. Okay, so the sine of pi over 6 is 1/2. Anybody remember what the sine of pi over 4 is? Yeah, root 2 over 2. And then the next one I'm going to look at is the sine of pi over 3. Anybody know that one? Yep, root 3 over 2. And then pi over 2 is 1. And then the numbers kind of, the ones I'm going to pick here, so you could look at 2 pi over 3. And what happens is stuff begins to come back down, right? It's that same thing of how, in the unit circle, stuff, our values went up to 1, and then they mirrored coming back down, and then in the third quadrant, they got negative, and in the fourth quadrant, they got negative. So if we started to draw the sine function here, right? So down here, we're at -1, up here, we're at 1, and so I'm going to go all the way out here at 2 pi, just to kind of put some things in perspective here. Pi over 2, pi over 4 would be half of pi over 2, and pi over 3 is, or pi over 6 is probably somewhere around there, and pi over 3 is somewhere around there. What you would find is that, so if we start to plot, so at 0, we're at 0. At pi over 6, we're at 1/2. At pi over 4, we're at root 2 over 2. So root 2 is like 1.4 something. So it's going to be a little bit bigger than 1/2. Root 3 over 2 is going to be even a little bit bigger. And then finally at 2, we're here at 1. So we kind of get this nice looking curve going on there. And that curve would actually repeat itself. So the sine function actually looks like this. And it keeps going forever. So the sine is what's called periodic, when that means the sine and the cosine function are periodic. It means it just repeats over and over and over again forever. So it's this nice gentle wave. It goes up and down, forever. Questions so far? No. Okay, so a couple things about the sine function. So this is, I should write y equals sine x. The domain. So remember, domain is what you can put in. So I'm telling you, it goes forever in both directions. So anybody remember how we would say what the domain is if it's going forever in both directions? Yeah, so it's going forever towards infinity. And then it's also going forever towards negative infinity. So the domain is, you could write it one of two ways. One way is you could write it minus infinity to infinity. Or you could say all real numbers. Right? Oops. Real does not have two L's. All real numbers. So it goes in both directions forever, either way. And then the range are the values that you get out. So what does it look like, my ranges? They're my y values. So my picture's not completely drawn to scale, but the range looks like it's what? Yeah, between 1 and -1. So from -1 to 1. And it gets brackets because it's including the -1 and the 1. So the basic sine, this is how the basic sine function looks. Its domain is minus infinity to infinity. Its range is from -1 to 1. It oscillates up and down. So this is the basic sine function. We're going to talk here in a second about the basic cosine function. And then what we're going to do is, if you remember from Math 126 and how you did all those transformations on graphs, so like we would stretch the graph and we might reflect the graph and we might like shift it left and right or shift it up and down. So we're going to do all those same things to this graph here. Any questions so far? No. Okay. So let me go to a new page here. Okay. So y equals, we're gonna draw the basic graph. So y equals sine x, y equals cosine x. So the basic shape for the sine graph is, and it's easier for me to draw it first and then label stuff. So it looks like this, right? Up here is 1, down here is -1. So it's between 1 and -1. And one complete wave. So starting, goes up, goes down, and comes back kind of to the starting position. So one complete wave would be this pink part here. Right? And so when you're in ALEX, when you're in class, when we're talking about the tests, so you have to be able to show me one complete wave. What happens to one complete wave of the function? And so the first thing here is that this here is 2 pi, just like I had before. This is pi over 2, and this here is 3 pi over 2. And so what I care about are these 5 points. So when it's time for me to graph the graph, I need to think about what happens to those 5 points. And so if we can show what happens to those 5 points, then we're going to be able to sketch our curve. And that's what Alex is going to ask you to identify 5 points. And so it's talking about these 5 points. So that's for the cosine, or that's for the sine. The cosine is actually really similar, except the cosine graph is basically the sine graph shifted a little bit. So it starts up here at 1. It looks like this. So this here is 1. This here is minus 1. Again, 2 pi, pi. Oops. I didn't do that right. We have to go back to, that's an okay spot to have labeled, but remember we have to go back to where we started, so it's got to come up here. So 2 pi, the middle here is pi, this point here is pi over 2, and this point here is 3 pi over 2. So when we're talking about the cosine graph, we're talking about the part that we want to concentrate on and figure out what happens is one complete wave on it. So start at the top at 1, go down, go underneath, come back up, go back up to 1. And the cosine graph has 5 points as well. So 1, 2, 3, 4, 5. And as we said, the domain on the sine graph was minus infinity to infinity, and the range was minus 1 to 1. Those are also the same for the cosine graph. So the domain is also minus infinity to infinity, and the range is also minus 1 to 1. Questions? No. Okay, so what we're going to do is we're going to transform the sine and cosine graphs, and we're going to look at either our functions or our graphs that we're going to graph are going to look like y equals a sine bx minus c plus, plus or minus d, or y equals a cosine bx minus c plus or minus d. Questions? And our problems are going to have actual numbers there instead of A's and B's and C's and D's. But this is going to be the generic part. And so we are going to, as we go through here, we're going to look to see what does the different letters represent. So what does the different letters do to these different functions for us? So the first one. So again, I'm going to put up here in the corner, we're looking at y equals a sine bx minus c plus or minus d, or y equals a cosine bx minus c plus or minus d. So we're going to look at those two pieces. So the first thing we're going to look at is what's called the amplitude. So the amplitude is going to be the vertical scaling factor So before, if you think back to Math 126, this would have been whether a graph is stretching or shrinking. So it's a vertical scaling factor, and it basically tells us how tall the wave is. Tells us how tall the wave is. And the way that we find it is that the amplitude is equal to the absolute value of A. If A happens to be negative, if A is negative, that means we are reflecting over the y-axis. Okay, so let's look at some examples, right? Because I just kind of gave you a bunch of words. So, for example, sketch the graph of A, y equals 3 sine x. Excuse me. Okay. So, A is the number that is in front of, that's being multiplied times the sine or the cosine function. So, do I have a number that's being multiplied times my sine here? Yeah. And what is that number? Right, it's a 3. So what that's telling me here is that my amplitude is going to be the absolute value of 3, which is just 3. Okay, so amplitude is saying how high the wave goes. So usually the sine wave goes from -1 to 1, but where do you think it's going to go now? Instead of from -1 to 1, where do you think it's going to go? Yeah, from -3 to 3. 2, 3, 1, 2, 3. Okay, so remember, when we go to graph, we always care about those 5 points. So each of those points is going to be basically stretched by a factor of 3. So I'm going to draw right now with a dotted line what the original sine function looks like, right? So remember, the original sine function would look like that, where this was 2 pi, this was pi, this middle point here was pi over 2, and this point here was 3 pi over 2. So that's the original sine function. But now we're interested in, and remember, it goes on forever, but we're just going to draw one period of it. So it's important, you're going to see it a lot of times just drawn with one period, but it does keep going forever. So these are my 5 key spots, right? And so I'm always interested in what happens to those 5 key spots. So we're stretching by 3, which means we're taking the y values and multiplying each of them by 3. So here, in my first point here, right, the y value is what? Whoops. My hand was moving as I was talking. But right here, when you're at the origin right here, what is the y value? Yeah, the y value is 0. So if I take 0 times 3, what's that going to be? Yeah, it's still 0. So my new y just still stays there. For this one here, my y value was a 1. And now, if I multiply 1 by 3, I get 3. So this new y value stretches up to here. Again, this one here is going to stay there because it's a 0. This one here was at -1, so it's going to stretch down to -3. And then this one is going to stay there. So my new graph here, so this pink curve here, that represents y equals 3 sine x. And so you notice I have these 5 points, right? So you're going to have to be able to label 5 points on your graph. Questions? So I should put a note here that basically what you're doing to figure out the amplitude is you're multiplying the y value on your key points by A. Questions? Oops, wait a minute. I have my sound, I guess, actually turned somewhat down. So okay, say that again.
Oh, okay. I don't understand what you're trying to show. Do you mind doing another one or going over this?
Yeah, we're gonna do another one. So what I did here was, here's my original sine function. And basically, before it used to go between 1 and -1, and now it's just going between 3 and -3. So I actually graphed this new function, y equals 3 sine x. And it's going now between, it's going as tall as 3 and as low as -3. But we're going to do another one. So B, y equals 6 cosine x. Yeah, so you wouldn't have to, on the test, you wouldn't have to draw me the original function if you didn't want to, if you just drew me that pink part. But yeah, how come the y in the middle point didn't change? Okay, so the y in the middle point didn't change because, remember, here the y value is 0. And so what's 0 times 3? Again, same thing here. The y value is 0. So what's 0 times 3? This is not, we're going to later on do where we pick the graph and we move it up 3. This is not moving the graph up or down. This is stretching it. So basically, the y values that were at 0 stay pinned at 0. And we're basically stretching that other part of the graph. Does that answer why there's those 3 values that didn't change? It's because if I took the y value there, 0 times 3, it's still just 0. Okay. Oops. No problem. So the cosine, right? Again, the cosine graph usually goes between 1 and -1, right? And it starts up here. So this is like that generic graph, right? That we talked about. 2 pi, pi, 3 pi over 2, pi over 2. And again, these are my 5 points. So usually it's between 1 and -1. So what do you think that 6 is going to do? Where's that graph going to go up to? Yeah, so it's going to go up to 6. 1, 2, 3, 4, 5, 6. Same thing. 1, 2, 3, 4. 5, 6. So here's -6. So again, this first point, the y value here was at 1. So 1 times 6 is now going to be 6. So it's going to come up here. It's stretching to up here. On this point and on this point, so these 2 points, the y value was 0. And so the y, and 0 times 6 is still 0. So this point's still going to stay there, and this point's still going to stay there. This point here was at -1. -1 times 6 is -6. So it's going to stretch down to here. And then this last point, it was at 1. So it's just like the first point, it's going to stretch up to 6. So the new graph is going to look like that. Right? So the graph basically is being stretched. Questions? No. So, well, I should say, the amplitude, what we're doing right this second, it only deals with the y-axis. Other things we're going to do deal with the x-axis. Does that answer your question, John? No problem. Other questions? Okay, so let's look at one more. So C, about y equals minus 1/2 the sine of x. So the amplitude is, again, the absolute value of minus 1/2, which in this case would just be 1/2. So, again, if you started with your normal sine function, the normal sine function goes between 1 and minus 1, right? So the normal sine function goes like this. It takes 2 pi to get back to where it started, right? And that makes sense because it's all, you're going all the way around the unit circle. It takes you 2 pi radians to get back to where you started. This is pi over 2, 3 pi over 2. So these are those key 5 points. And so this is going to take us kind of 2 steps to do. So the first thing we're going to do is we are going to worry about making it, so since the amplitude is 1/2, rather than go between minus 1 and 1, now we want to go between minus 1/2 and 1/2. So again, these points that are at 0, they're always going to stay there at 0 when we're dealing with the amplitude, because 0 times 1/2, 0 times 6, 0 times 3, all of them is just 0. This point here used to be at 1, so when I take 1 and I multiply it by 1/2, it comes down. Same thing, this point here used to be at -1. When I take -1 and I multiply it by 1/2, it's going to come in closer, so it's going to come in here at minus 1/2. And I'm going to draw this pink graph dotted because it's still not the final graph. Right? So the pink graph is just, all we've done is we've taken care of the amplitude. But if you remember, I said if your A was negative, you also have to reflect it. So reflecting it means basically making a mirror image over the y-axis. So this point, the mirror image for all of these points on the axis, they're just going to stay. But then this top part here, instead of being up here, is now going to come down here. The mirror image is down here. And this part that was down here, the mirror image is now up here. So, whoops. Not the greatest arc I got going on here. Okay, so this point got reflected and that other point got reflected. So the green graph is the answer here. So I flipped it over. So after I did all those points, I just flipped over what I had. Questions? Yeah, put something in my mouth here. Yeah, so if it's negative, we flip it over. Yep, we reflect. Other questions? No. Okay, so that's all the stuff that deals with A. So A is going to change how big it is, and then it's going to potentially flip it over. So now we're going to worry about what B does. Okay, so remember, again, we're still dealing with these y equals a sine bx minus c plus or minus d, y equals a cosine bx minus c plus or minus d. Okay, so the period, when we're talking about a sine or a cosine function, the period is how long it takes for one cycle of a trig function to be completed. So, like, when we were talking before about the regular old just sine function, it took 2 pi to be completed. Same thing with the cosine function, right? It started up here. To get back to that same spot, it takes 2 pi. So it's one complete cycle of the wave, right? So in general, it's 2 pi, but as soon as you start putting a b, if there's a value for b, that gets changed. So the period for sine and cosine is 2 pi over b. So it's 2 pi over b because 2 pi is how long the regular wave is. And basically the b, what the b is doing is so if you think back to Math 126, it's basically stretching or shrinking horizontally. So it's a horizontal stretch or shrink. And when you horizontally stretch or shrink, you affect it by multiplying or by basically dividing by the factor you're stretching or shrinking by. So back in Math 126, when we would horizontally stretch or shrink, we would multiply or we would divide the x value by the factor that we were stretching or shrinking. So we're taking the original period, which was 2 pi, and we're dividing it by the factor that we're stretching or shrinking. So it's all of this stuff is really, even though it seems very new, it's really actually just Math 126 stuff applied specifically to the trig functions. But because it's very useful in trig, we give it all kind of new names. Does that help, Liana? No problem. Okay, so when you find, so usually when we do the period of the wave, we would say out here, we used to say, right, it was 2 pi, and then we would say this was pi, this was pi over 2, and this was 3 pi over 2, right? And those were the same for both the sine and the cosine. Because really all that we're doing is we're taking the area between 0 and 2 pi, and we're splitting it up into 4 equal sections. So if we call P, so if we let the period be equal to P, so I have 2 pi over B, so this end place will always be P, and then we're splitting this into 4 equal parts. So when I split it into those 4 equal parts, this middle part is always going to be 1/2 of P, right? I'm splitting it in 2, so I'm splitting stuff into 2 pieces. This first one is then I'm taking that 1/2 piece and splitting it again, so I would get 1/4 P, and then this other spot is, it's the 3/4 spot of P. So I put this here because this is like the quick way to figure out what you should label your axes. Once you figure out what your period is, we're going to figure out a quarter p, a half p, 3/4 p, and then that's how we're going to label our axes. And you might go, I have no idea what you're talking about, but I'm going to do an example, and hopefully it makes more sense then. So, for example, sketch a graph of A, y equals sine 4x. So in y equals sine 4x, this 4 is my b. So my period is going to be 2 pi over b, or 2 pi over 4, and I can reduce that to pi over 2. Questions? No. Okay, so I'm going to want to sketch this graph, right? This graph is a sine graph, so we know our sine wave goes like this. There was no number in front of the sine, so we're still just as high as 1 and as low as -1, right? So that's only going to change. It's only going to be something that's not 1 and -1 if you... if there's a number in front of that amplitude to change. So that's the first thing. The second thing is now I know that this end spot, this is P, so this is going to be pi over 2. And remember, I need to label this spot, and this spot. So I know the end is pi over 2, but I have to find labels for those other 3 spots. And the way that I'm going to do that is that's where I'm going to use this stuff here. So I'm going to need to figure out 1/4 of P, 1/2 of P, and 3/4 of P. Some of you guys might be able to just look at it and be like, oh yeah, I know what a half P is. I know what a quarter P is. I know any of them. Some of you guys might need to actually do it out, so it doesn't matter to me. Do whatever you need to do to get the problem. So if I look at 1/4 P, that's going to be 1/4 times pi over 2, or pi over 8. So this first spot here is pi over 8. Questions about how I got anything so far? No. Okay, the next spot is 1/2 of P. So 1/2 of P is going to be 1/2 times pi over 2, or pi over 4. So this next spot here is pi over 4.
So we're basically just multiplying across?
Yep. So remember, when you have a fraction, if you have 2 fractions times each other, you just multiply across the top, multiply across the bottom. And then I need 3/4 P. So it's going to be 3/4 times pi over 2, or 3 pi over 8. And so here are those 5 key spots. So for me on a test, as long as it's very clear like this that I know what your spots are, you don't have to actually write down the points for each of them. But let's write down the points here, because when you go to Alex, you're going to have to put those points in. they're not always nice numbers, so you can't always just, click on the graph. You sometimes have to use, there's a little tool that, in ALEKS, it kind of looks like this. It's kind of got like a little grid, and then it's got like a little X, and it's basically telling you want to plot a point. So if you click on that, it'll bring up an XY pair for you to type in the X and type in the Y, and it'll plot that point. So this first point here, this is the point 0, 0, right? I'm 0 on the X and I'm 0 on the Y. This point here on the X, I'm at pi over 8, and on the Y, I'm at 1. Here at the X, I'm at pi over 4, but I'm at 0 on the Y. Here I'm at 3 pi over 8, but I'm at negative 1 on the Y. And then finally, I'm at pi over 2, 0. So you would need to enter those 5 points into ALEKS. And then ALEKS has a button that you click, and once you put those 5 points in, it'll just make the curve for you. Questions? I'm getting some no's to questions. Okay, let's try another one. So b, y equals the cosine of 1/3 x. Okay, so again, there's a number in front next to that x. This is that b. And so it's going to change my period. So my period is going to be 2 pi over b. So in this case, that's 2 pi over 1/3. So remember, if you're multiplying or if you're dividing by a fraction, you have to do keep, change, flip. So keep the top, change the multiplication, flip over the bottom. So it's now times 3 over 1. Remember, you can always think of this as 2 pi over 1. So on the top, I have 6 pi, and on the bottom, I have 1, and so that's just 6 pi. So my new period here is 6 pi. So if I think about drawing, the cosine function starts up. Okay, so yeah, so we're going to worry about if b was negative later on. We're going to do that at that's going to be one of my very, very last examples. So I'm not sure we're going to get to it today. So can b be negative? Yes, b can be negative. However, when you're dealing with sines and cosines, I'm going to teach you how you can always make sure that the b is not negative. And so then if the b is not negative, we can figure out what to do. It's easier to deal with it if the b is not negative. It's not to say you can't, but I just think it's actually easier to deal with all positive b's. And so because of that, we don't have to, we're not going to worry about b being negative, because at the end of class, probably not today, but the end of Wednesday's class, I'm going to tell you what happens if b is negative. Does that answer your question? Okay. Other questions? No? Okay. So, I pulled up the guard so I won't accidentally move ahead a page here. Okay, so this end spot here, this we know is 6 pi. And then we have to find 1/4 of p, right? So again, we're labeling these places. So 1/4 of p is going to be 1/4 times 6 pi. So if you think about it, right? 2 goes into 4 2 times, 2 goes into 6 3 times. So, And again, remember, you can always think of this as 6 pi over 1. So on the top, I'm going to be left with a 3 pi, and on the bottom, I'm going to have a 2. So this is 3 pi over 2 is that first spot. We can look at a half p. So 1/2 times 6 pi. So again, 6 pi over 1. 2 goes into 2 one time. 2 goes into 6 3 times. So this is going to be 3 pi. 3/4 p. So 3/4 times 6 pi. Again over 1. 2 goes into 4 2 times. 2 goes into 6 3 times. So this is going to become 9 pi on the top and 2 on the bottom. So I didn't label it, but this would be 3 pi, and this is 9 pi over oh, excuse me, 2. Thank you. Thanks. And again, this up here is 1. This down here is -1. So we've got these 5 points. Sure. Yeah, I can. Is there anything you need me to go over again, Morgan? Can I show the last slide? Sure. You guys can, like, if I move to a next slide and you're not done copying or something, just tell me to wait up a minute. No problem. Okay, so let me know when I can move from this slide. And then I'll go to the new slide. It's very hard, right? Because when I'm in the classroom... Okay. Is everybody okay for me to move to the new slide?
Hold on 1 second.
Sure. Yeah, it's really hard, right? Because in a classroom, I can see you guys writing, so I know to, like, slow down. And so I try to do some things when I'm, like, teaching here, but it's just not the same, right? Because I can't see you writing. So, yeah, so if I'm ever, like, going to, you know, if I move to the next page and you can't see anything, like, let me know. It's not a big deal. Okay, so if we go to the next slide, right, then that's the one we were on here. So, other questions about how you change the period of things? And what we're going to do is we're going to eventually build stuff up. So we're eventually going to be doing problems where we're doing all of these transformations, or a good chunk of the transformations in one problem. So before we move on, I just want to do one problem that kind of has both of the transformations that we've done so far. So C here, let's do y equals 2 sine of 1/2 x. Or actually, let me write it a little differently, because sometimes you'll see it written this way. How about 2 sine and 1/2 is probably not a great one. Let's do a quarter. X over 4. So in this case, I have an A value where I'm stretching something. And then I also have where I'm changing the period. So one of the first things to notice is that x over 4, so exactly, that's exactly what I was going to talk about, Liana. So x over 4 is the same as saying 1/4 of x. So my 1/4, that's my B, and the 2 here, that's my A. Okay, now, the period and the amplitude are kind of some of the easiest transformation pieces. So I usually just take care of both of them at the same time. So just like in the last two examples, we figured out, right, I have a generic sine function. So my sine function usually looks like this. And we know that we have to kind of figure out what these 4 spots are. Right? So let's do that part first. Let's figure out what those 4 spots should be. So our period is going to be 2 pi over B. So it's going to be 2 pi over 1/4. So 2 pi times 4 over 1, or 8 pi over 1, or just 8 pi. Okay, after solving for P, why do I put 1/4 P? Okay, so the reason I figure out the 1/4 P, the 1/2 P, the 3/4 P, is because I'm trying to figure out what these 4 labels are. And so these 4 labels, this one here is 1/4 of P, this one here is 1/2 of the period, this is 3/4 of the period, and then this is the whole entire period itself. So that's why I figured those, like these 1/4 P's, 1/2 P's, 3/4 P's out, so I know what to put on these labels here. Does that help? Because it's like I've taken that chunk of the axis and I've split it into 4 equal parts. And so since I split it into 4 equal parts, the first one is always going to be 1/4 P. The second one is always going to be 1/2 P. That third one is always going to be 3/4 P. No problem. So this out here is the 8 pi. It's the P. Right? So if I do 1/4 of P, it's going to be 1/4 of 8 pi, which would be 2 pi, right? Because 4 goes into 4 one time, 4 goes into 8 2 times. So this first spot here is 2 pi. The next spot is 1/2 of P. So it's going to be 1/2 of 8 pi. So 2 goes into 2 one time, 2 goes into 8 again. 2 goes into 8 4 times. So this is going to be 4 pi. And then that last spot is going to be 3/4 of P. So 3/4 times 8 pi. So 4 goes into 4 one time, 4 goes into 8 2 times, and then 3 times 2 is 6. So this is 6 pi. So I found what the period was. The period was 8 pi, and then I split it up into 4 equal sections. Questions? Okay. So remember, we have 5 points that are pretty important, right? These 5 points. So I figured out the x values, right? I have the 8 pi, the 2 pi, the 4 pi, the 6 pi here. But now I need to figure out how high it goes and how low it goes. But remember, so usually it's as high up as 1 and as low as -1. But in this case, we changed the amplitude. So remember, there was a 2 here. So how high should it go? Yeah, so it should go up to 2. So this point here is going to be too high, and this point here is going to be too low, so minus 2. So rather than, like, I know before when we were dealing with the amplitude, like, we drew it and then we, like, stretched each piece. But this is more how I do it. So I just draw the basic curve that I'm looking for. If I'm dealing with a sine function, I draw a basic sine curve. If I'm dealing with a cosine function, I draw a basic cosine curve. And then I worry about the period, and then I worry about the amplitude. Questions? So if it doesn't have a number in front of the sine or the cosine, it's always going to be from 1 to minus 1. No problem. Other questions? Yeah, you could do it that way. You can always do the B first and then the A. I could have drawn the curve and put the A up there first. And then did the B, but either one is fine. Does that help? Other questions? No. Okay. Okay, so if you're doing a problem, and we're going to talk about this too when we put them together. So, we haven't talked about vertical shifts yet. We're going to, hopefully today. But vertical shifts, right? Take the whole entire graph and move it up or down. That has to be the last thing you do. So you have to do everything else first, and then you deal with the vertical shifts. So the first two things I do when I'm dealing with drawing a sine or cosine function is I do what I have here, what we've done so far. I do the amplitude and the period, and I kind of do them at the same time together. So that's the first thing that I do. The next thing I'm going to do is shift it left or right, and that's what we're going to do next, and that's called a phase shift. And then the last thing you would do would be a vertical shift up or down. Does that help, Alex? No problem. Other questions? No? Okay. Okay. So the next thing, as I kind of hinted at, is what's called a phase shift. Okay. So, again, if we look at y equals I'll write the cosine first this time. It doesn't matter. Cosine of bx minus c plus or minus d. And y equals a sine of bx minus c plus or minus d. Okay, so horizontal shifting left or right in terms of a trig function, because it's a wave, we're shifting the phase of the wave. So the phase shift is really just a fancy way of saying we're shifting left or right. And the amount we shift is C over B. So we shift C over B. If C is positive, we're going to shift to the right. If C is negative, we're going to shift to the left. But the thing is that to be able to do this, you have to be really careful. Inside, you have to have a minus C, okay? And you might go, well, what happens if it's a plus? I'm going to show you. But we're going to work to make it look like a minus c for us to figure out. So we're going to always be subtracting something off. And this is the reason why back in Math 126, you might remember it's like, oh, if I had like minus 7, it went 7 to the left. And if I had, or not minus 7, if I had minus 7, it went 7 to the right. And if I had plus 7, it went 7 to the left. So it kind of did the opposite. It's that same deal, but the reason it's doing the opposite is because you're always thinking of it as minus a number. So, for example, sketch a graph of A. Y equals the cosine of x minus pi over 2. Okay, so the only thing I have here, right, in this problem here, I don't have a different b to begin with, right? My b in this case is just a 1. It's a little weird, but my b, if you think about it, there's a 1 here in front of the x. So my b is a 1, and then I do have that subtraction sign, and so this part here that I'm subtracting off, that is my c. So in this case, our phase shift is going to be c over b. So pi over 2 over 1. And if you divide by 1, you haven't done anything, right? So this is just pi over 2. So what that means is everything in our graph is going to get shifted pi over 2 to the right. Okay, so we're going to shift pi over 2 to the right. So the first thing I'm going to do is I am going to draw the basic cosine graph. I'm not going to shift anything. So I've got my basic cosine graph. I know that my basic cosine graph goes out here to 2 pi. That this is pi over 2. This is 3 pi over 2. So that's my basic graph, right? And it has these 5 important points. I'm just giving people, I should say, like, you guys were probably like, okay, why is she not talking or saying anything? I was just giving people a minute to catch up with me before I do the next part. So, each of my points is going to move pi over 2 to the right. Right? So, if you happen to notice, in this case, pi over 2 happens to be each of these tick marks on my axis is another pi over 2, right? From here I went to pi over 2, 1 pi over 2. I moved over another pi over 2 to get to pi. I moved over one more pi over 2 to get to 3 pi over 2. I move over one more pi to get to 2 pi. So first, before I do anything, it might be helpful if I label a couple more spots on my axes. The quick way to do that is to notice this is saying I have 1 pi over 2. Whatever your first spot is, that's how your axis is kind of labeled. It's basically saying that I'm working right now in terms of pi over 2's. So I have 1 pi over 2, and then I'm going to have, so 1, 2 pi over 2's, but 2 pi over 2 is still just pi. 3 pi over 2's, 4 pi over 2's. So my next spot would be 5 pi over 2's. And if you wanted to even label a couple more, the next one would be 6 pi over 2's, 7 pi over 2's, and you can keep going. Now, 6 pi over 2, you could reduce, right? 6 pi over 2, this is really just 3 pi. But the idea is whatever your first thing is, so since my first thing was a pi over 2, I'm counting off by pi over 2's. So it's saying I have 1 of these, I have 2 of them, 3 of them, 4 of them, 5 of them, 6 of them, 7 of them, and so forth. So each spot has to slide pi over 2 to the right. So this first one here, it slides pi over 2 to the right to get to that next spot. This next one slides pi over 2 to the right. This next one slides pi over 2 to the right. Slides pi over 2 to the right. Slides pi over 2 to the right. So each of those slots slid over a pi over 2. So I'll draw my graph here in blue. So the final graph we're looking for is this blue graph here. Right? I just didn't want you to think that those arrows from the sliding were actually part of the graph. And when you're drawing it by hand, you'll see it gets a little misshapen, right? Like it doesn't look as great of a cosine curve anymore. That's okay. As long as you kind of have the right general shape and you've got your points in the correct place. I'm pretty lenient in terms of the test. In Alex, it'll draw the curve for you, so it'll make it really nice. Yeah, so we ended at 5 pi over 2 because it was pi over 2 past the 2 pi, so past that last point. So it went over pi over 2. Does that help, Liana? No problem. Other questions? No. Okay. Should we try another one? What about B here? Y equals the sine of 3x minus pi. So again, right, here's my B, and I'm subtracting that pi, so here's my C. So in this case, again, in this case, since my B is not a 1, I've actually changed the period first, right? So the period, we said, is 2 pi over B, so it's going to be 2 pi over 3. Right, so originally, I've got a sine function, right? This is 2 pi over 3. I need those 4 slots just like before, right? So I need a quarter times 2 pi over 3, which is going to be pi over 6, right? Because the 2 and it cancels there. So we end up with pi over 6. So that's that first spot. Why did I circle 6 pi over 2? Oh, I just circled 6 pi over 2 because I said that you could reduce it down to 3 pi. In that last example. I need a half of p, right? So a half of p would be a half of 2 pi over 3. So the 2's would cancel, so we'd get pi over 3. So that's this middle, whoops. This middle section, pi over 3. And I need 3/4 of p, so 3/4 times 2 pi over 3. So again, 2 goes in 1 time, 2 goes in 2 times. The 3's would cancel, so we get pi over 2. So this is pi over 2. And I didn't change the amplitude, so, and I should have labeled that over here. This is 1, and this is -1. So same thing, 1 and -1. And I've got my 5 dots. So all I've done so far is I have made the sine curve, and I took care of the period and the amplitude. And now I'm going to figure out the phase shift. So again, I have that minus c. So our phase shift is going to be c over b. So in this case, it's pi over 3. Okay, so what that means is in that graph that I have drawn right this second, I need to move everything over pi over 3. If you notice, I kind of always looking from the beginning. So my beginning here is at 0. Pi over 3 is 2 slots over, right? So this point needs to go 1, 2 to pi over 3. It's moved 2 slots. That means each of these remaining points also has to move 2 slots. It also means I need some more places on my axis. So again, how did you graph the black line on the first example if we didn't solve anything known? Okay, so if you were just given, if b is a 1, then it's always going to be 2 pi. How long it takes is 2 pi. Now, I said from the beginning that's 2 pi, which is, and I put what the other ones were. It was a half pi, 3 pi over 2. You could use my same, if you know p is 2 pi, you could do the 1/4 p, 1/2 p, 3/4 p. It's just that we end up drawing that original curve so many times that usually you end up just remembering, oh, it's 2 pi, it's 2 pi here on the end, which means it's pi over 2 pi, 3 pi over 2, 2 pi. It's basically the corner points of the unit circle, right? So it's like every essentially 90 degrees. 0, 90 degrees, which is pi over 2, 90 degrees, which is pi, another 90 degrees, which is 3 pi over 2, and then back to the end, which is 2 pi. So that's why I didn't draw them for the previous example. So here on this example, I need to label some more things on the axis. So if I look, I'm working in pi over 6s here. So each one of these tick marks is another pi over 6. 1 pi over 6. 2 pi over 6s. 3 pi over 6s. 4 pi over 6s. Now 4 pi over 6 happens to reduce to 2 pi over 3. So I can label this would be 5 pi over 6. 6 pi over 6, right? But 6 pi over 6, that's really just pi. 7 pi over 6. And you could keep going, right? As many as you need. And so now I'm in a position where I can slide this graph to the right. So each of these pieces moves to the right pi over 3, which means it moves 2 slots. So this first one moved 2 slots to here. This second one moves 2 slots to here. the dot that was here moves 2 slots to here. This point moves 1, 2 slots to here. And finally, this last point, which is under here, moves 1, 2 slots to here. So we're talking about this as our new graph, that blue one there. Right, and I can make it, oh, maybe I can't make it. I thought I could make it thicker. But basically, right, you're talking about this being our new graph. Questions?
I don't know if you answered this before, but in the chat I asked why you circled 6 pi over 2.
Yeah, I thought I did, but so the reason there wasn't anything special about it. I was just trying to say that 6 pi over 2 actually becomes equal to 3 pi. So I just circled it when I reduced it.
Oh, okay.
Other questions? No.
How do you get like the second part, like the 5 over pi over 6 and
So I got the 5 pi over 6 by, again, looking at the original thing, it was pi over 6s, which means along my axis, everything is a pi over 6. So really what's happening is this is saying I have 1 pi over 6 in this first spot, right? But 1 pi over 6 is just pi over 6. This is saying I have 2 pi over 6s, but 2 pi over 6s reduces to pi over 3. This is saying I have 3 pi over 6s, but 3 pi over 6s reduces to pi over 2. This is saying I have 4 pi over 6s, but 4 pi over 6s reduces to 2 pi over 3. And then 5 pi over 6s, right? 6 pi over 6s, 7 pi over 6s. So I'm literally just counting off. So I'm starting with 1. So basically I'm saying it's kind of like if you think about if you were lining up a bunch of apples and you were like, I have 1 apple, 2 apples, 3 apples, 4 apples, 5 apples, 6 apples, 7 apples. Same thing, except our apples here are pi over 6s. So I have 1 of these pi over 6s. I have 2 of these pi over 6s. I have 3 of these pi over 6s. I have 4 of these pi over 6s. I have 5 of these pi over 6s, 6 of these pi over 6s, and 7 of these pi over 6s. Does that help for that question?
yeah, so you're just basically counting up.
I'm just, counting up. So, okay, wait a minute. Let me answer these questions in the chat. I know, like, we're a minute over class, so if you need to go or you don't want to hear answers to these questions, feel free. Okay, so let me see what ones I missed here. So, yes, Jolena, C does tell us that we have to shift. So if there's a C value, you're going to have to shift left or right. So John, the steps are, and we haven't gotten through everything yet. So once we get through everything, I actually will list out the exact steps. But the thing is that the steps are, the first thing you would do is you take care of the amplitude, and the period and reflecting. You take care of the amplitude and period. Then if you need to reflect, then you do the phase shift. So that's kind of the steps that we're working on. And then the reason why we didn't calculate the period in the first example is because here it's just a 1. So your period, you could calculate it, it's 2 pi over b, but b is just a 1, so it's just 2 pi. So it hasn't changed from the very basic sine function or cosine function here. Does that answer everybody's questions? No problem. No problem. Anything else? And just a reminder, like, you guys should have gotten that email from me, but I'm not having office hours this afternoon. I have a meeting I have to go to, but I will have office hours the rest of the week. And if you're planning on coming today and then you can't come to any of my other office hours, just shoot me an email and we'll find some time that I can meet with you.
So this problem's already solved. The 3 doesn't matter right now?
So say that again. Like, what do you mean, the 3 in front of the X?
Yeah.
So we used the 3 that was in front of the X. So we used it in finding the period, right? So the 3 that's in front of the X is used in 2 different places. So one, it's used to find the period. So that's what told me I had 2 pi over 3. And the second place it's used is in the phase shift C over B. So it's used, like, we did use that 3, but we don't need, like, there's nothing else we have to do with it.
No, I confused it for the amplitude. That's why I was like, why is it moving?
Oh, right. Yeah, the amplitude would be another number out in front.
Yeah, I confused it right now.
No problem.
Thank you.
No problem.
That's it.
No. So, Liana, we do not have class next Monday on President's Day, and I will hopefully remind you guys of that on Wednesday. But yeah, there are not classes on President's Day, so we don't have class that day. No problem. See you Wednesday. I don't know off the top of my head. I have no idea off the top of my head how many topics there are. But when you log into Alex, it'll tell you. So, like, every time you go into Alex, it'll tell you exactly how many topics are due that week. And yeah, it is due on Friday. Yep. No problem. Have a good one.
Can you jump back into the examples for periods?
Okay. So these guys? Or the first one? Here's the first one.
Yes, that one. Yeah.
Okay.
I kind of don't understand this concept at all.
Okay. So the period, first off, just tells you how long it takes for the curve to get all the way from the start to the end. Yeah, in Alex, there are, so give me 1 second, Kelly, and I'll talk about this. In Alex, there are periodic knowledge checks. It's just to make sure that, like, you understand what you're getting, so that if you later on, if there's something you didn't understand and you need it to do a future homework, it'll bring it back to remind you about it. They don't counter your grade or anything. Okay, so, Kelly, here, the normal, just the basic sine function, it takes 2 pi to get there. And the reason it's 2 pi is because when you go all the way around the unit circle, it takes 2 pi to get all the way around the unit circle. So the basic period is 2 pi long.